we can start this delayed first session of the afternoon. So all the speakers are here, and so I will be happy to start as soon as possible. The first keynote talk is delivered by Professor Steigmann, which is well known to everybody, working in mechanical engineering, of course. And the title of his presentation is Mechanical Response of a Fabric Sheet to Three-Dimensional Bending, Twisting, and Stretching. So, Professor Steigmann, please.
Thank you very much. It's a pleasure to be back here. I was here 2 years ago in connection with another meeting. Better? Yeah. And I recognize several people. I'm here visiting Professor Dell'Isola at La Sapienza in Rome. And I'm incidentally here in connection with my visit to him, to work with him. We have an interesting collaboration to study the macro scale manifestation of micro scale mechanics. So one system that we're interested in studying is, say, a material composed of fabric. So you have interwoven yarns of a fabric. And on the microscale, you can imagine these are somehow mechanically behaving like beams, perhaps with extension and bending resistance. And their interaction with each other manifests itself in interesting ways on the macro scale, which is perhaps unexpected. Another similar structure is a Pantograph Ik Lattice. So you have a microscale consisting of flexible beams, flexible and extensible beams, which are connected to each other at pivots at their points of intersection. And they can rotate about the pivot as they deform, perhaps deforming in space in 3 dimensions. Imagine they lie on a surface and deform in 3 dimensions. They pivot about a common axis, which we can take to be the evolving normal to the surface. And mechanically, these two systems, fabrics and pantographs, exhibit many common features. So we will model them both in a single framework. Professor Dell'Isola and his group have shown me some fascinating simulations based on a discrete lattice of beams, many beams crossing each other, connected at internal pivots, and subjected to some overall boundary conditions, global boundary conditions. And these simulations show some very interesting and unexpected phase segregation behavior, some localized internal deformations that are quite unexpected and rarely encountered in solid mechanics. So he gave me an assignment, which I'm trying to pursue here, which is to imagine or conceive of a continuum analog of this discrete microstructure. He's shown me recently a beautiful 3D printed manufactured pantographic structure, which also experimentally exhibits the features that he group has simulated using this discrete microstructural model. So my job is to conceive of a continuum model, like a plate theory, 2-dimensional theory of an elastic surface, which is capable of capturing these interesting features exhibited by the actual material. One of the immediate problems we encounter is what kind of continuum theory to use. So for example, in the literature on the mechanics of fabrics, which is based, I think, entirely on more or less classical nonlinear plate bending theory. And this suffers from a fundamental defect, which I try to explain. So you imagine a sheet consisting of fibers, perhaps like so, maybe macroscopic, orthotropic, and classical plate bending theory will affect the intrinsic bending stiffness of these fibers only when the surface changes its shape. Classical plate bending theory accounts for bending stiffness only if the shape of the surface changes, the embedding geometry of changes. I'm holding this incorrectly, I think. It completely fails to account for a fundamental mode of elastic resistance, which is in-plane bending of a fiber, like so. So if the surface remains flat and we bend the sheet in plane, then we will have this so-called geodesic bending, geodesic curvature of the curve. And the standard theories completely suppress this effect, which, however, clearly mechanically relevant because the fiber does not ask, are we bending it out of plane or in plane? It will offer an elastic flexural resistance in both cases. This calls for a generalization of the continuum modeling because geodesic bending, we know from differential geometry, is associated with metric in the surface and also the gradient of metric in the surface. And this is a purely metrical property of the geometry. So this kind of bending is a strain gradient effect, which exists even if there's no change in shape in the surface. This kind of bending is described by classical theories. This kind is suppressed. So it calls immediately for a modeling framework based on strain gradient elasticity. So we have in mind a constitutive sensitivity not only to strain, but also to gradient of strain at any material point. And it's this gradient of strain that generates geodesic bending, among other effects. So I'll just sketch some of the basic ideas. Oh, I hope so. Stretch it, yeah. I don't know. Let's see. Can it be stretched? Okay, so the basic tool is a classical differential geometry of surfaces. The kinds of curvature I've just described are embodied in this kind of kinematic descriptor. So we have a position field on the surface, 2 coordinates parameterize the surface, and the comma, alpha, beta are partial derivatives with respect to those surface coordinates. And this is the classical Gauss and Weingarten equations in differential geometry. This is the embedding geometry or the curvature due to change in shape of the surface. And we have here these connection coefficients, Levi-Civita connection coefficients. Or I suppose if you're from Northern Europe, they would be the Christoffel symbols. And it's this part here that accounts for this geodesic bending in a certain manner. Okay, and okay, we can do some things with these concepts. We can introduce a metric. We can introduce fiber directions. So capital L and M are the initial fiber directions prior to deformation. Small l and m are their trajectories after deformation, and lambda and mu are stretches induced by the deformation. And we can also define an angle of shear if the fibers are shearing. This is also associated with metric or strain in the surface. Too much notation, so I will simply give a more descriptive discussion. And the shearing induces a local area change or a local areal stretch in the surface. And the second fundamental form we can resolve into components. These L alpha, L beta, and so on are the initial basis. The fibers, we'll use the fiber directions as a basis to decompose the curvature. We have normal curvature of one fiber, normal curvature of another, and then twist of the fiber. That's due to this kind of effect. You bend the fiber and simultaneously, you bend the sheet and simultaneously twist it. The embedded fiber will be twisted in the process. And we imagine that these embedded fibers are like spatial elasticae or Kirchhoff rods, which offer elastic resistance to flexure as well as twist. So this will be important in the response. Okay. So geometrically, the notion of geodesic curvature I mentioned here is associated with the rate of change of the direction of a fiber along the fiber, the fiber direction. So the rate of change of the tangent as you move along the fiber generates geodesic curvature, one component, and also if the surface is changing its shape, there will also be a normal curvature of that fiber, and likewise for the other family of fibers. So geodesic curvature is associated with the rate of change of a fiber trajectory as you move along that same fiber. Also relevant in this subject is a little-known notion of so-called Chebyshev curvature, which is associated with the rate of change of one fiber as you move along the other family of fibers. And this is something that we don't normally see in mechanics of surfaces, but it turns out to be relevant for us. And this also includes the twist of the fibers. Okay, so we imagine each fiber is like a spatial Kirchhoff rod. The rod, regarded as a one-dimensional continuum in its own right, responds constitutively to a curvature twist vector that characterizes the rate of change of an embedded triad of vectors in the rod. For example, the tangent and two vectors in the cross-section. As we move along the fiber, these generate flexure and torsion, and we have a constitutive sensitivity or elastic resistance to this kinematics. And so that's just characterized, for example, for one family of fibers, characterized by a vector containing these curvature and twist components. What we can do is, for example, if you have a Pantograph Ik lattice, as the surface deforms in 3 dimensions, the two families of the pantograph pivot about a common axis, the normal. This effectively means that the normal to the surface is embedded in the cross-section of the fibers. And this allows us to express kinematics associated with the twist in terms of surface geometry alone. And so, in principle, although a Kirchhoff-type rod theory is like a Kossara continuum, the nature of the interactions of the fibers is such that it becomes effectively a pure surface theory describable entirely by surface position and its gradients. So, for example, one of these two flexure components are associated with normal bending and geodesic bending of a fiber. And then we have the third component associated with twist, which after some tedious calculations, which I'm going to skip here, can be associated ultimately with the embedding geometry, the shear straining in the fabric, and this torsion or twist of the surface itself. Okay, so ultimately we can relate everything to the surface geometry alone. Okay. I mentioned before these Levi-Civita connection coefficients as accounting for geodesic curvature. They do so in a way, however, not quite in a physical way, because the Levi-Civita connection is not itself tensorial. So we want a tensorial kinematic descriptor if we're to have a meaningful constitutive theory. The variables appearing in it should have a tensorial structure. So we can generate such a variable by comparing the connection coefficients after deformation to those prior to deformation. And if we use a single convected coordinate system that tracks the motion of the surface, this difference turns out to be tensorial, a third-order tensor. And so it offers an appropriate kinematic descriptor. And in fact, it's nothing other than components of the second gradient of deformation. And this kappa is a kind of a pullback or a referential version of the embedding geometry. So it's also a kind of a strain measure. Okay. Okay, so we can decompose these variables into components along the fibers, and in doing so, we're led naturally to certain kinematic variables that are relevant in the theory. One that embodies geodesic bending, as well as some possible gradient effects of the stretches, geodesic bending and some other effects. Gamma here embodies these Chebyshev curvatures and other terms. Ultimately, this is determined, although it's not obvious here, ultimately this gamma is determined by the cross derivatives of fiber stretches. So imagine you have a family of fibers say parallel, horizontal fibers. And locally you have a stretch, let's say, of, say 1 approximately, so a fiber is unstretched. A transverse derivative of the stretch in this direction will force the neighboring fibers, parallel fibers, to either lengthen or contract, and that will engender a kind of energetic mode of response. So this variable gamma accounts for that, and that too is a strain gradient term. Okay, so these are the relevant kinematic descriptors, and there's too much notation here, so things simplify a bit if you take the fibers to be initially straight, then there's some simplification. You can see here the geodesic curvature and a tangential stretch gradient, geodesic curvature and another tangential stretch gradient, and then this gamma. This equality is a compatibility condition that comes from the presumption of C2 continuity of the deformation field. And this involves the cross derivatives, or the orthogonal derivatives of stretches, okay? And embodies that effect I mentioned. Okay, so we can decompose then our relevant kinematic descriptor, this is second gradient effect, in terms of these geodesic and normal bending terms and this gamma term I mentioned. Okay, so then we come, that offers a kind of a short kinematic description of the model. We need some constitutive equations. So we'll suppose that there is an elastic response or a hyperelastic response embodied in the form of the strain energy function, an areal energy density, an energy per unit area of the sheet, reference area. And what we want to do is write that as a linear form in the variation of the position. So we have a one-parameter family of deformations, and U is its variation in the sense of a virtual displacement, let's say. If we want to write that ultimately, the variation in the energy, as a linear form in the first and second gradients, taking appropriate care about the tensorial structure. This is a covariant derivative here. And if we're successful in doing that, then we have the response functions. Okay, so what we have here is an orthotropic strain gradient sensitive sheet. So we have here a conventional elastic sheet, for example, classical plane stress, and these are the strain gradient terms. And we can make an argument that they should appear quadratically, as shown here, because they embody scale effects already. So all these terms have dimensions of 1 over length squared. If we non-dimensionalize those expressions by a local length scale, say the thickness of a fiber or the spacing of a fiber, then these non-dimensional variables will in practice always be small enough to justify retaining only quadratic terms. Okay? So there's no assumption of kinematic linearity here. This comes purely from dimensional considerations. The leading order effects will always be captured by these quadratic terms. Okay, and this conventional energy accounts for fiber stretching and also fiber shearing, and elastic resistance to shearing. Okay, and then we have some parameters which are adjustable elastic moduli, flexural stiffnesses, torsional stiffness, and other stiffnesses associated with geodesic bending and so on. Okay, so we want then to use that energy to extract constitutive equations essentially for these response functions, which are the work or power conjugate terms in this expression here. Power conjugate to the variation of the virtual work. That's easy to do. It's a kinematic exercise. I won't trouble you with it. At the end of the story, let me find something conceivably interesting. We get these response functions. These are force type variables, and these are moment variables. These moment variables account not only for the normal bending, as in conventional plate theory, but also the in-plane geodesic bending as well. And we can use virtual work then to extract the appropriate forms of the equilibrium equations if we want to. That procedure essentially imitates the procedure initiated by Kirchhoff in deriving classical plate theory by variational methods. And this is simply a generalization of that. So what we have here, rather than go through that procedure, we can summarize the result. This is force equilibrium. The divergence, a divergence structure. And T alpha are given here by this combination of these force-like terms and a divergence of these moment-like terms. For example, in elementary beam theory, a divergence of a moment is a force, essentially, a shear force, so it enters into force balance. Okay, so we have the basic structure. We can extract boundary conditions, a la Kirchhoff, although the context here is more general. And we have a model, and I want to show you some simulations that have been obtained just today and yesterday by Ivan Giorgio, an associate of Professor Delisola. I hope I can find it here. There's a file stored in the file here. So let's see. That's it. Okay, the top one. The top one. Yeah. So here's a simulation. This is a finite deformation. Initially a rectangular sheet with fibers horizontal here and vertical. The sheet is tilted 45 degrees initially. And we control the displacements at these two ends. No forces or couples are applied anywhere else. And simply extend this by finite deformation. And what I want you to observe is something very interesting. There's actually an elaborate phase phenomenon taking place here. Here we have a uniform strain triangle adjacent to the boundary. Here another uniform strain region with a different amount of shear and its twin over here. And then another interior uniform strain state with again a larger amount of shear. So we have essentially three phases: uniform strain with a different amount of shear, and another uniform strain with a larger amount of shear. And the material is intelligent. It knows that the way to minimize its energy is to get rid of the bending energy as much as possible, because it's a positive definite term. If we can get rid of it, if we can suppress bending, we can suppress energy. So over most of the domain, the bending is actually suppressed by this effect. But to accommodate the transition from one of these phases to another, we must have localized transition regions in which there is localized bending of the fibers. I don't know if you can see it easily here. The bending is quite localized in a, say, finite but small width internal transition layer, like a boundary layer, except it's not at the boundary. It's offering an interpolation or a transition between these uniform strain phases. We cannot connect these uniform strain phases directly to each other, because that would require a kink forming in the fiber. There the curvature would be locally infinite, and with flexural resistance that would be an unbounded energy solution. So to maintain finite energy, we must have some bending, but to minimize it, we localize that bending as much as possible in these very narrow layers. So this high-order geodesic bending effect is actually essential in accommodating the minimum energy state that would otherwise not be possible. Okay. And so this is, Ivan just obtained this result yesterday, the numerical simulation using COMSOL, multi-physics finite element code, which directly minimizes the energy. It doesn't solve the Euler-Lagrange equations. And the theory is arranged to automatically ensure the existence of a convergent process, convergent finite element solution. And what's interesting is that this phase coexistence behavior, which you would which is a kind of elaborate macroscale manifestation of a very simple microstructural mechanics. It's quite unexpected. It's actually borne out by experiments on fabrics. Professor Delisula will show those to you later. And by experiments on an actually fabricated 3D printed pantographic structure. So watch later on today for this kind of phase coexistence, which is predicted by the theory, entirely inaccessible using the typical approach based on nonlinear plate theory. Okay? This is all geodesic bending here, an inherent strain gradient effect. I wanted to show one more quick file before stopping here. I may need your help again. Sorry. Thank you. And this shows essentially the same effect, but now we exploit the full potential of the model to allow excursions into 3 dimensions. So we have an elastic surface which is being twisted. Now we rotate this far boundary to induce a 3-dimensional bending. So not only do we have this persistent phase segregation behavior with these internal transition layers, but we also have the twisting resistance of the fibers being accommodated by the change in embedding geometry curvature of the surface itself. And so this is quite a robust theory. Computation time is quite minimal. We've captured the essential features exhibited not only by discrete mesoscopic, or you could say microscale simulations, but also the experiments in terms of these internal transition layers connecting the constant strain states. But also, there's an enormous advantage in computational effort vis-a-vis actually meshing each one of these fibers as a 3-dimensional body in its own right with appropriate links or pivots connecting them. Okay? Ivan Giorgio has also done that calculation, and the results are almost indistinguishable as far as the surface mechanics is concerned. Computational time is orders of magnitude shorter in this case. So we have essentially a new shell theory or plate theory, taking into account the geodesic bending among other strain gradient effects. It's quite faithful to the simulations based on microscale mechanics as well as experiments. Thank you.
Thank you. Are there any questions?